In this video, we're going to introduce a new function, the quadratic function. If you think about it, during test one, we worked with linear functions. And that function or that equation was in the form of y equals mx plus b, where m was the slope and b was the vertical intercept. Then test two, we had exponential functions that were in the form of y equals ab to the x, where now the a was the vertical intercept. And now we have quadratic functions in the form of y equals ax squared plus bx plus c, and the c is the vertical intercept. So let's begin with an example. You're on top of the Sears Tower, which is 1,450 feet in the air. From the top of the building, you drop a baseball. The function here, which is this h of t equals negative 16t squared plus 1,450, this will give you the height of the ball at any given time. So if I said, what is the height of the ball at time 0, I would take 0 for time and substitute that into my equation, where t represents time. And I would be left with 1,450 feet. And if I were to say, well, what's the height of the ball after 1 second or 2 seconds or 3 seconds? This equation should give me the position or the height of the ball for any given time. So the first thing we're tasked with is to fill in this table. Now, the long way to fill in the table would be actually manually take the number 0, sub it into the equation, get an answer. Sub in 1 to the equation, make the calculation, get an answer, right? Put the 2 in for t, square it, multiply by negative 16, and so on. The quicker way would be to actually use our graphing calculator and enter into y1 the function. So we're going to enter negative 16t squared plus 1,450. So here's my function. And again, make sure you use the negative key, which is found below the number 3, not the subtraction key. Okay, and I want to create a table. So my table in the book starts at 0 and ends at 10. So I press the window key, because above window it says table set. And I want to start at 0. I'll count by ones, and I want this to be auto. So now I press second and graph, because above graph says table. And these are my values, right? So 1,450 feet, 1,434 feet. And you can see as time gets bigger, the height of the baseball becomes smaller, right? And eventually it's going to hit the ground. So somewhere between 9 and 10 seconds, the height is 0, so the ball would be on the ground. So let's complete this table. Hopefully your table looks something like this. And again, I took these values directly from my calculator by graphing the function and then creating a table. So now let's look at question 1b. We're asked, how far does the ball fall during the first second? Well, from 0 to 1, that's the first second. So if I subtract these two heights, that should tell me how far it fell. So it looks like the ball falls 16 feet in the first second. And then in the second second, right, from 1 to 2, we have to do the subtraction. And it looks like the ball fell 48 feet. So in the first second, it falls 16 feet. In the second second, it falls 48 feet. So it looks like the ball's speed is increasing. It's accelerating. Because in the same time frame, the ball's traveling a greater distance. On the next page, it says, using the height function, determine the average rate of change. So you remember the slope or the average rate of change was the change in output over the change in input. In this case, our output is the height, our input is the time. So if I go back to our table and I create 2 points, maybe 0, 1450 and 1, 1434, where this would be my y2 and my y1 and my x2 and my x1, or think of this column as my output column, my input column. To find the slope, we do the subtraction, and we end up with negative feet per second, negative 16 feet per second. And in the second second, right, so from 0 to 1, we have negative 16 feet per second. And in the second second, From 1 to 2, we have negative 48 feet per second. All right, so think about it. Feet per second is the velocity. So the speed of the ball is 16 feet per second and then 48 feet per second. So like I said, it's accelerating. The negative sign just indicates the direction. If we had a positive 16 feet per second, the ball would be going up. When the ball's going down, we have a negative 16 feet per second. Okay. And then part C says, based on the results, do you think we have a linear function? And of course, our answer is no, because the average rate of change is not constant, right? Our slopes are not constant. Earlier, I think in test 1, we conducted a test to determine if we had a linear function. And for us to have a linear function, we need the same slope or the same average rate of change. And in this case, our average rates of change are different. So we do not have a linear function. Next, we're asked to graph the function, and they give us a window. So I take out my calculator. We've already put our equation in to create the table. I'm just going to change my window. So I press the window key. I'm going to use their window. Negative 10 to 10 for x min and x max, and negative 50 to 1500 for the y min and y max. So I press window. So here's the window that they've given us. And by the way, the x scale, that just tells you what we're counting by. So from negative 10 to 10 on the x-axis, we'd be counting by 1, so there should be 10 tick marks in either direction. I could change my scale here, maybe to count by 150 to reduce the number of tick marks. If you leave it at 1, that's fine. It's just going to be really bunched when you press graph. You know, you're going to have over 1,500 tick marks going up and down. But the bottom line is our graphs look the same, right? So that's the first video in this series. Look for the part 2 shortly.